Christoph Englert. You can call me Chris. Better that way. I apologize to everybody who were expecting a different guy here. Okay, talking about the Higgs. Not related to him. Maybe I am, I don't know. You have to buy me a drink at the bar to find out the details. This is normally how I do it. So I'm going to talk a little bit about Higgs physics and Higgs phenomenology, both in the standard model, but hopefully about BSM aspects of the Higgs as well. That obviously has some overlap with some of the things that you will hear over the next few weeks as well. So obviously it will have, I'm not going to mention any particular relation to dark matter or supersymmetry. I guess there are specific lectures about that by Paddy and other people. But of course, touch a little bit on effective field theories. So of course you have Tim Cohen's lectures about effective field theories. Those are relevant. If you're into your effective field theory, you have Michelangelo, Mangano talking about future colliders. Of course, the Higgs is sort of a new player in town, and whatever new detector concept or collider concept that we might be dreaming about, the Higgs will have a fairly central role in the motivation of that experiment in the future. So this would be future colliders. And of course, we'll have Kieran, when or if he shows up, about perturbative field theory. So perturbative QFT, which probably means QCD. And rounding things up is my mate Frank Krauss telling you everything you need to know about quantum chromodynamics at colliders. Yeah. All right, so please ask questions, interrupt me at any time. I will try to answer all your questions. If I can't do it, I'll make something up, all right? And then it'll be up to you to find out whether I'm telling the truth or not. So why are we talking about the Higgs? So why did Tillman and Tracy invite me here to bore you with things that are already, yesterday's sensation, maybe tomorrow's calibration? Most probably. Well, the Higgs is really special because it's a 40, 50-year-old story, and it's a unique discovery in the sense that it was anticipated. And the Large Hadron Collider was put together as a machine specifically to find the Higgs, amongst other things as well. But it's really designed to detect the Higgs, because it was the last missing piece of the standard model and is at the core of what we believe might be the next step towards a more concrete or a more complete theory of particle interactions beyond the standard model. So let's start off with a little bit of an introduction, how that all came together. So you can, in principle, go back to Fermi's theory. So this is a super successful theory of beta decay. That was 1934, if you like. And it's essentially a non-renormalizable theory. Okay, people didn't worry about this in the 1930s, but certainly worried about it in the 40s. With the introduction of quantum electrodynamics, okay? So some intuition by Bethe, and later on formalized by Feynman and all the famous guys who won the Nobel Prize. They found that quantum electrodynamics, and we'll discuss about this in due course, is a renormalizable theory, so it's super predictive. You can calculate it to all orders in perturbation theory, no problems whatsoever. Now, this doesn't really fit in here, so this is non-renormalizable. And, well, this is perfectly renormalizable. And of course, the question is now, you have two successful theories, one describing beta decay, another one the theory of light in its very quantum sense. And of course, our task as theorists is try to sort of combine them in a nice way and to end up with a philosophically satisfying picture. So the question is really, can we unify these? And that was difficult, and it took a while to figure out how this might come about. Now, people these days don't really worry so much about non-renormalizability, because we have a much better understanding of quantum field theory than in the early days, when there were a lot of competing theoretical concepts on the market besides quantum electrodynamics and QCD. But what certainly changed the pace of this whole story was the discovery of neutral current interactions, and that was in the Gargamel bubble chamber. So which is essentially, it was an effective interaction, but as you all know, it's mediated through the Z boson. So we have neutral current interactions. So the way this was discovered was that you had an incoming neutrino split up into an E plus E minus pair, and then just an additional neutrino left the bubble chamber. So it couldn't be a photon. The neutrino has no electric charge, so it had to be something different, but it couldn't be massless, because otherwise we would have seen it already. So this really prompted people to trying to sort of understand how this can come about. And of course, massive vector bosons or massive vector mesons are a possibility to sort of write down a potential UV completion to whatever interactions you've seen there. And so this was at CERN. You've been at CERN, some of you, already? Hands up if you have. Have you seen the Gargamel bubble chamber? It's outside the theory complex. You can climb into it. Some drunk Russians tend to do that and sleep in it, but that's a story for a different day. So that was in 1973, and then the story is always in experimental physics, and I'm afraid particle physics is an experimental strand of physics, if you wish. So we live off discoveries and not understanding them. And so that was 1973. So two experiments were devised then in the 80s, UA1 and UA2, to specifically look for these for the nature of these neutral current and charged current interactions. So those were eventually found, W's and Z's, in 83 at UA1 and UA2. Okay, so, and those are massive spin 1 bosons. Essentially coming back to the very top of this blackboard here. Now the question is, how can you actually accommodate massive vector particles or massive vector bosons in concepts that feed into renormalizable theories such as quantum electrodynamics? Okay, so how can we accommodate these in perturbative QFTs? Right, and it's very often in theoretical physics that the solution was already there in the literature. So the solution to that, or the answer, was already there in the 1960s. So in particular, in 64, you had Peter Higgs, my colleague from Edinburgh, and the Belgian duo Brout and a guy named Englert. And of course, then politics sets in, and you have to worry about who is left out. So should you add Anderson to this as well? Done similar work on in solid state physics, but probably it's politically only apt to mention here Guralnik, Hagen and Kibble as well. Okay, so this was the whole idea of spontaneous symmetry breaking, and we'll talk about this in quite some detail. Okay, so if you look up these papers, they're written in a completely different language, but it's clear that all the technical details were not fully understood at the time. Okay, and especially the issue of gauge fixing in spontaneously broken gauge theories as a whole beast in its own right, and we're probably not going to talk about this in too much detail, but I'll certainly mention the differences between symmetry breaking of gauge theories as compared to symmetry breaking of global theories, because that's really, really different. But then again, this is just essentially the concept of avoiding massless scalar fields if you break symmetries, okay? And putting this together then is, of course, the famous Glashow, Salem and Weinberg model, which was 74, so 10 years after this, which is essentially the desired unification of Fermi theory, ultraviolet completion of Fermi's theory with quantum electrodynamics. And this is really where we deal with Electroweak. 67. Well, I mean, I just pick one random date from Wikipedia. So let's do it like that. That's always the danger with quoting exact year numbers. You'll always get them wrong. 74, 75 sounds like a really boring Cornell song. All right. Well, if you don't agree with my numbers, that's fair enough. I wasn't around at the time, so. So the whole idea and the way I set this up is that we sort of trace the steps and explore a little bit the pitfalls of these discoveries, and then making our way to the standard model. And the Higgs, of course, is the only thing that was left as an implication of this mechanism that hadn't been discovered before 2012. All right, so let's move on with, unless there are any questions, okay, about the history of electroweak symmetry breaking. Good. Well, I'm relieved. So let's talk a little bit about the abelian Higgs model. So in essence, we just try to work our way to the full theory here of the standard model using one particular example, which is not really the full thing, but the idea is that we can use these concepts and just generalize them to the case in the end that we are mostly interested in. So the starting point here is really that you have gauge theories, okay? So you all came across gauge theories, I suppose, in electrodynamics. This is where it starts, really. So you start from Maxwell's theory. You write down the electric and the magnetic fields in terms of potentials, assuming that they are defined everywhere in space. You deal with a topologically trivial space-time, so you can define potentials everywhere. And then you see you have this additional residual ambiguity of defining this vector field and the scalar field. And that's certainly quirky in electrodynamics. makes calculations easier, but it has no real fundamental insight, okay? That came later on when people tried to sort of understand these gauge freedom transformation in the context of quantum theory with, say, the Schrödinger equation. So the way we understand this today is really that this gauge principle is the fundamental ordering principle behind interactions in particle physics. And so it certainly is the foundation of particle theory today. And a direct implication of that is that we deal with massless gauge mediators. So we have massless force mediators to all orders in perturbation theory. And this is really the crucial motivation behind looking at gauge theory. We know that to good approximation, the gluons are massless, the photon is massless. Somehow we have to tell our theory that it should stay like this. Okay? And that's the only way of doing this in perturbative theory for vector particles. So the U1 QED case is particularly instructive for that. So U1 highlights the crucial properties of this. So you essentially start with a Lagrangian. There's -1,4. So normalizations really don't matter here so much, but it's working canonical normalization where you have these two field strength tensors. You patch them together, and F mu nu, as you probably know, is just a commutator of two gauge covariant derivatives. And for us, this will be minus IE A mu. Well, this depends on all space-time. So now that everything is abelian, of course, this just reduces to a d mu a nu minus a d nu a mu. And that's everything that you need, really, to understand the gauge bit of quantum electrodynamics. So this Lagrangian, by construction, is invariant under local U1 transformations. So if you send a mu of x to a mu of x minus a d mu alpha of x, where alpha is just a real valued scalar field, then this thing is invariant, okay? So that's just the QED story that we started with in the 1940s. So now this is of course broken if we look at stuff or the phenomenology of sets and W's. So if we now believe that we can do the same trick here, again just for vector mesons that are massive now, for vector fields that are massive, then one way of doing this is just by hand adding a mass term. Let's just pop this up a little, which is a ma squared divided by 2 a mu. So if you plug this into the Euler-Lagrange equations, you get back the Proctor equation. So this describes a massive spin 1 vector field. But of course, this symmetry now is broken. Okay, so while this is somewhat accidental in Maxwell theory, you could say, why should I care? Okay, I just write this in to my Lagrangian, I'll take it from there. But you end up with a theory that has very bad perturbative behavior. So you will end up with all sorts of issues that are partially mendable in the U1 case. but you can not generalize this to non-abelian gauge theories, okay? So when we try to do the same trick, just writing in bare mass terms for the W's and Z's by combining them into SU2 gauge representations, this will not work at all anymore. So then everything will just go pear-shaped. Okay, so this breaks U1. And this is certainly not what we want to have. So the question why we should care about this comes a little bit later, okay? Or the answer to that. Of course, the answer to this is then spontaneous symmetry breaking. Which essentially means in the context of gauge theories that we dynamically introduce masses. Okay, so this means mass cis through interactions. Okay, so let's have a look at this. Not doing the full belay, but just a little bit of a warm-up exercise, just looking at it heuristically. So if you look at your free propagator in QED, okay, so without bookkeeping all the Lorentz indices and the metrics and your personal convention of what signs you choose, then you can write this as a minus I divided by p squared minus 0, okay? So it's just the inverse of the Fourier transform, so it is just of this operator, it's just the Green's function. And this 0 just shows you that there is no pole shift, so the photon stays massless when you start with everything. So now if we were to introduce some interaction here, okay, and essentially you couple the photon to a constant background field. How do you do this? By assigning some characteristic coupling strength, and here by anticipating what's coming on later, writing this as a g squared, and this background field expectation value with a phi. Then this will change the properties of my free theory, okay? So perturbation theory tells me then I have to look at the Dyson resummed propagator. So I start off with the free theory, then I do one insertion, I do two insertions, and so on and so forth. Okay, and just by entering this here, if I say that this is it's a I sigma of p squared, which is only allowed in a Lorentz covariant theory, only allowed to depend on whatever momentum comes inside here, and I choose that this does not depend on the momentum because it's a constant background expectation field, I'll just take this as Ig squared phi. Okay, so then writing this in terms of these Feynman rules, what I end up with is a I divided by p squared. That's this term, plus an I divided by p squared times a g squared times I times phi. Okay, let me just get the dimensions right here. So it would be a phi squared from this part, the interaction, and now, so we're doing just a full 2-point function here. Okay, so if I p squared, minus sign here, minus sign here, minus sign. So as petty, I'm not worrying so much about minus signs. We'll correct them while we're moving on. And so the reason why I chose this with plus is, of course, that these guys cancel here. So plus additional terms. So what it boils down to is something like I divided by pi squared. and the geometric series, okay? G squared, phi squared, divided by p squared to the power of n, where n runs from 0 to infinity. Okay, so now this is not worrying too much about convergence. We never really do. You can resum this entire term into the final result of the geometric series, and you have I divided by p squared, 1 divided by 1 minus g squared phi squared divided by p squared. So now multiply the p squared in, and something quite magical happens. I have now a propagator that has a shifted mass pole. Okay, so I started off with a free theory that has no masses, but I introduced some interaction of this field with some constant background field, whatever that might be. And if that order parameter is non-zero, then as a consequence, I get a shifted pole. And this is exactly how you can introduce masses into interacting gauge theories. Okay, so the whole idea will be now to sort of come up with a field language that gives meaning to this heuristic picture here. So the pole is shifted, and if you were to write down an effective theory that contains, that is built from these 2-point functions, you would end up with something that describes the Procka equation. So we managed to introduce masses here, okay? So the summary that we can take away from this is that if we manage to somehow create a situation where we have massless vector fields and they couple to some sector that has a non-zero vacuum expectation value, then we'll get mass terms for free. Okay. And the only possibility that we have really at our disposal without automatically violating Lorentz covariance or Lorentz invariance on the basis of the Lagrangian density is doing this through scalars, right? Otherwise you just break the Lorentz group as well. So now let's do this in field space. So what we need is like a scalar, and we somehow have to couple it in a nice way to these existing vector fields. Okay, so the only way to introduce a well-behaved scalar is if that scalar transforms under this U1 gauge symmetry. Okay, so a Lagrangian density that you could write down is again this d mu phi dagger d mu phi, okay, minus a potential that depends on phi. Now if we assume, and implicitly we do this, that phi transforms linearly under this U1 symmetry, then really that potential can't be a function of phi alone. Okay, so it has to be a function of phi dagger phi. Otherwise you violate gauge transformations if you send phi to phi e to the I alpha of x. Okay. All right, so what we can do now is write everything down every term that we can come up with up to mass dimension 4 to have a theory that is, ad hoc renormalizable. Okay, maybe I just go over there. So generic ansatz that you can come up with, phi dagger phi, is a mu squared phi bigger phi plus a lambda phi bigger phi squared. Okay. So and that adds on top of whatever gauge stuff that we have already introduced. So in order to apply perturbation theory, this is really what we want to do in the end. We have to find the minimum of the energy and the minimum in field space to fluctuate around that and apply perturbation theory. So what we need to do is find the minimum of V, and because there are no other dynamical degrees of freedom that have a mass or have a potential in this particular model, it really boils down to finding the minimum of this potential here. So that's of course really standard undergrad physics. You end up, if that is 0, then this means that phi squared is a minus mu squared divided by 2 lambda. So now we have two choices here, and these choices depend a little bit on whatever sign we allow our mu squared to have, and of course whatever sign we allow our lambda to have. Okay, so we want a theory that's stable, so this means we can't have a negative sign for the lambda, otherwise we don't really have a stable vacuum, tunnel into like nowhere. So this automatically is really ruled out on first principle basis, if you wish. So the only parameter we can play with is this mu squared. So the choice that we have is we can have mu squared bigger than 0. Then this doesn't really work, okay, because this is a real number. So real numbers are ordered. Can't get a modulus that is negative. So this just amounts to making a mistake whilst calculating the minimum of the energy. So what we really are dealing with here in that case is just a massive scalar that is coupled to quantum electrodynamics as a gauge theory. Okay, so it would be a charged massive scalar. Nothing wrong with that theory. Okay, so this is QED plus a massive scalar. That's of course charged, but it's a bit of a boring thing. That's not really what we want to achieve, because in that case the minimum of the potential will sit at phi equals to 0, and this is not the situation we would like to achieve. Okay, so more interestingly, but slightly weirder, is if we really have a tachyonic mass term. So if mu squared is smaller than 0, get a positive number here on the right hand side, and we really have a vacuum configuration that prefers a non-zero vacuum expectation value of that scalar field. So what we get with this is QED plus vacuum expectation value that is not equal to 0. Okay, so everybody should shout here, because this is what I'm doing here is I'm actually not allowed to do. Okay, so we are dealing with something that is tachyonic. Yeah? And this is really the true genius behind spontaneous symmetry breaking and gauge theories, is to avoid all the problems that normally come in when you have tachyonic particles in your spectrum. It just doesn't really work out in a quantum field theory sense. But here it does, and it does more on top of that, because you'll get vector masses, and actually this is the only way of writing down vector masses in a way that everything stays renormalizable to all orders in perturbation theory. That's Cornwall, Levin, and Tiktopoulos, also in the 1970s, if I'm not mistaken. Okay, so what we'll have here is a picture that essentially we deal with the potential that arbitrary units. In our case 1, That's the boring case. Looks like this. Now case 2, that's the more interesting bit, where we now sit here for our field phi, and to do perturbation theory, we just look at small fluctuations around that particular minimum. So, coming from all of this line of argument, we can continue now with case 2 and just see what happens. So, first of all, let's just rewrite this phi squared here in a slightly nicer way. So that's a minus mu squared divided by 2 lambda. But of course, as many of you know, you write this just as a v squared divided by 2. And if you compare this now to our little Feynman diagram picture that we started off with, you just enter here a v squared divided by 2, and you see that this way you create a photon mass of g squared or e squared times v squared divided by just e squared. Yeah.
Having a scalar tangent mass is the only perturbative normalized way to. What's the statement?
So it's a bit preemptive because we're going to talk about this probably tomorrow in a little bit more detail. But the U1 case, as I said, is special. But if you do this with, say, non-abelian gauge theories like SU2, that's what we'll do in the end. So we have 3 degrees of freedom here in the broken case. So we have 2 transverse polarizations of the photon, and the mass creates a longitudinal one. Now you could think of just writing down the mass term just by hand and not care about the implications of violated gauge invariance. So what you see is then that the S matrix has a bad energy behavior at high energy. So you break unitarity. And so what Cornwall, Levin, and Tiktopoulos did is they just reversed that question. Said, let's study the high energy limit of general S matrix elements and reverse engineer from that what the Lagrangian can look like if that in high energy behavior is good. And if you do that, then the only way the Lagrangians that are picked out are the ones that are generated by spontaneous symmetry breaking. So this really makes a strong case for the Higgs mechanism as such. So
what exactly are the ingredients you're trying to preserve? Normalizability, perturbativity, unitarity?
Yeah. Well, I mean, these are, renormalizability and unitarity, those are delicately intertwined.
But it's perturbativity that I'm
yeah.
curious about. I mean, are there
well, if you give up on perturbativity, then of course, you have to revert to the lattice really to give you any quantitative statement. But what the Electroweak sector has told us so far, not just at the LHC, but pretty much every Electroweak precision experiment that has been conducted before that, is that the Electroweak sector behaves exactly like a perturbative theory. Yeah. And we talk about this in some detail as well. We're studying a little bit Electroweak position observables and all that sort of stuff. So it really was before that already a perturbative paradigm. And then the LHC as a multi-billion arbitrary currency experiment was really constructed around perturbative quantum field theory, contextualized with spontaneous symmetry breaking. I think that's something to be fairly amazed at. And the best thing is worked, Okay. Otherwise, it would be a bit catastrophic. Anyway, so now because phi is just a complex scalar, we can rewrite this. Phi as some normalization factor e to the I chi of x v plus h of x. So you just make a choice essentially here. So the choice is that we pick our vacuum expectation value to be aligned with the real axis. So You can think of this field configuration selects a circle in the complex plane. What we're doing is we're picking this particular spot here, and then the chi fields just measure how often we go around in the circle. Okay, and under these U1 symmetries now, what will happen is that these chi's will have to transform non-linearly. Just if you write down an e to the I alpha, you'll see they add up, so they transform non-linearly. So mass terms will not be created for these fields. So everything to here is really doing spontaneous symmetry breaking of global symmetries. So nothing is really special to the quantum picture of gauge theories here. So, and this is typically where we as phenomenologists or as theorists, use the spontaneous symmetry breaking as a slight, it's really an abuse of language, as you wish, if you wish. Because it really is something different, okay? So the vacuum here is completely gauge invariant, and it is not for spontaneously broken global symmetries, and the implications are quite different. And this is where all of this, comes together in a nicely orchestrated kind of way. But back to our original Lagrangian now. So we can now just plug this guy into our Lagrangian density, and we end up with quite a few terms now. So we have a minus 4 f mu nu. So the kinetic energy of our photon field, we have E squared V squared divided by 2, A mu. So the mass terms as we wanted. From this here, expanding this out in the kinetic term of our scalar field, we get a kinetic term for that boson field plus a mu squared h squared. So remember that mu squared is smaller than 0. Okay, so at least this is a correct sign. Not sure about the others. We have left over some interactions for these chi fields. D mu chi, plus all sorts of interactions between chi and h that I'm not interested in at the moment. But more importantly, and this is what I want to focus on a little, is a mixing term of h mu and a derivative of these chi fields. Yeah. E to G. Yes, I mean, coming from this Dyson resum 2-point function, yes. Yeah. Because now we're doing QED, so you identify this coupling constant as the electric charge. But of course it's arbitrary, it's only like after you measure it, you know what parameter to give a meaning. All right, so first of all, this is quite annoying because we're not really there. So when you do perturbation theory, you want to have like free theories at the kinetic level. So you like that stuff, bilinears in fields and their derivatives, gives you the free theory, and then everything else is just fluctuations around it. I'm sure that if you haven't heard already about it, I'm sure Kieran will tell you a little bit about it. Maybe. But of course, this is not very welcome here, right? Because now we have a tree-level mixing of this vector field and a derivative of this chi field, which chi field would be exactly a Goldstone boson, okay? But here it's so it's massless. there's a 0 here in the bilinear term of the chi. All right, so now the question is, how can we get rid of this? And this is where you have to make a choice, pretty much like making a choice here, which is align everything with one particular direction in field space, and you make a similar choice of adopting linear combinations between A mu and chi. So if you now look at the gauge transformation of this Lagrangian under the U1 transformation properties, you can do that. It's quite a lengthy calculation, but you'll see everything works out. Okay? And this term is really crucial, so you need it. But, of course, it's not very welcome if you want to do perturbation theory, as I already said. So the way you handle this is by rotating this term away. And so rotate. Which essentially means that you can choose a U1 gauge transformation that's just alpha x is equal to minus chi of x. Okay, then this guy is gone. But then you sort of have used up all the freedom that's there, then this chi is gone from the theory. But it has it delivers crucial ingredients to making this whole thing gauge invariant, okay? Because you adopted one particular gauge choice, but that is not more motivated than any other. So the way you do this now, on the basis of Lagrangians, this is quite interesting, this whole idea of arc psi gauge fixing. So you add a term here to the Lagrangian. So we fix the gauge, and we fix it in such a way that we add a gauge fixing Lagrangian, which is a minus 1 divided by 2 psi d mu a mu plus a psi ev squared. Okay. So essentially, if you do Maxwell's theory in your Jackson course, you will, when you introduce the free solutions of light as an electromagnetic wave, and you do this in terms of potentials, then you often choose d mu a mu to be 0, and you use the freedom in this additional alpha rescaling to achieve exactly that. So this is just a little bit of a variation of it, where we allow it now to have like a value that that is proportional to this gauge fixing parameter psi. Okay, but if you square that out, what you'll see is that the psi cancels in the mixing term, and then you can partial integrate it, and this will cancel exactly this mixing term. But of course, you're stuck with the psi dependence in both the square term of d mu a mu and the square term of the chi field that I forgot here. Okay. So your theory will know what you've done to it, okay, and it might not like it, because you can see that this d mu a mu term, I said this before, so a mu transforms with this with the shift. So it's not really clear, and actually it's quite apparent that you're violating your gauge principle with this term exactly. Okay? So you might get away with doing your calculations in the end and see that you basically bookkeep this parameter psi, and you make sure that the final result does not depend on it. Okay, but this is sort of a leap of faith. And this is really where, when I don't know really what how Kieran is going to introduce perturbative field theory, if he's doing it in the canonical way or if he's doing it just purely QCD or with a generating functionals. So this becomes super clear if you use generating functionals. And you can see that you actually have a much larger symmetry in your gauge-fixed Lagrangian that sort of tells you that this choice will never matter. Okay, so you get a set of associated ward identities. So it's really a supersymmetry that you see there is BRST invariance. And this will supply you with a set of ward identities that tells you that this will never matter at any order of perturbation theory. Okay, so this is quite a deep field theoretic insight into gauge fixing, really. And there are properties to these transformations. We don't really have the time to go into it. But this is really where things completely depart at the quantum level when you deal with spontaneously broken symmetries in a global sense or with spontaneously broken symmetries in a gauge theory kind of sense. Okay? Because you will always have this additional stuff that will tell you that your theory is still well behaved. And even more so, what this mixing term tells you, and it relates to your question, and a little bit that discussion that Cornwall, Levin, and Tiktopoulos said now, in order to preserve renormalizability, if you just were to introduce a longitudinal degree of freedom and a mass, a bare mass for the photon, you would see that you run into all sorts of problems concerning power counting arguments when you do perturbative field theory expansions. But here, this already tells you that at high energies, this particular polarization that you introduce through the interaction with the Goldstone bosons, at large momenta behaves essentially like a scalar field. And this reintroduces the good properties in power counting, and thereby this theory will be renormalizable. Of course, formalizing this discussion was worth a Nobel Prize, so I can't do this in one sentence, okay? But this is essentially what's happening here, and this is the true magic behind spontaneously broken gauge theories. Are there any questions? Or am I boring you to death? Yes? So, one of the issues if you just write down a massive, just introduce a longitudinal polarization by hand, is that at large energies or large Euclidean momenta, the vector field starts behaving a little bit like a ghost. And essentially you lose either perturbativity, depending on what you want to give up, or you lose renormalizability. It's just a basic scaling argument how Feynman diagrams scale in the very ultraviolet regime. But what this interaction term tells you is that essentially it's not really a vector at high energies, but it's a derivatively coupled scalar. And that avoids all of the issues that are associated with the bad behavior of vector bosons in the ultraviolet regime. So to really see that, you have to sort of work through a loop calculations. We will not do this, but the electroweak sector is, perturbative series expansion in the electroweak sector is really a formidable thing. QCD is a boring theory. It's hard, okay, and that deserves recognition in its own right. And I say this as somebody who did their PhD in QCD, okay. So this feature is something is compatible with the gauge transformation is compatible with a significant non-vanishing vacuum expectation value, introduces a nice sort of crosstalk between different terms in the perturbative series expansion. And of course in QCD you don't have that. That's why QCD is a bit boring, but it's good because if QCD was like QED probably, or like electroweak theory, we wouldn't have this conversation now. So on that term, I sort of enjoy QCD as well. Yeah. Mhm.
for SU2, we get more than one.
Yeah.
So we have fixed the gauge using different theta parameters, but we have only one gauge fixing parameter even if you write the propagators, right?
Yes, yes, yes. So the question is, if we now have, I'm doing this here with one field, what happens if you have deal with more than one vector field? In the case of SU2, you have 3 would-be Nambu-Goldstone bosons that get eaten here by the vector fields. So first of all, they will transform in a given multiplet. They will transform in the adjoint. So this is sort of fixed. However, maybe Tim is going to say a few things about that. But if you start messing about with the global symmetries in your Lagrangian, then at the dimension 6 level, so if you add some additional terms in that might arise from integrating out heavier states, then you have to consider different gauge fixing conditions for different fields. So then this becomes a relevant thing, and then it becomes technically highly involved. But for the standard model piece, you get away with doing it with one parameter. Okay, so essentially, what I was trying to say is that we have to make sure that this choice of our gauge fixing parameter psi does not impact calculations at the end. I can't do this here, but there are associated word identities that guarantee that this will indeed be the case. Okay, and we can talk about this later tonight. I don't know. But here we want to do Higgs physics and not so much electroweak physics. So, if we have a look at the propagators now that you would get for these vector fields in the gauge fixed version, you find the delta A mu nu equals a minus I p squared minus ma squared, where ma is just given by the term that I showed you there. And g mu nu minus 1 minus psi divided by p squared minus psi ma squared p mu p nu. So this would be for finite psi. So in this already you can see what really happens here. So that propagator for a psi that's not equal to 1 will introduce a growth with energy, right? So plug them into a loop, then you really have to worry about these terms because they will introduce additional singularities that can't be absorbed in any of the other terms, naively. But they do because of the dedicated interactions of this A field with the associated psi's and ghosts and so on and so forth. For the choice, well, for finite psi, you also have a propagator now for the chi fields. And then this is an I divided by p squared minus EV psi squared. So you can see that in that combination, you're now only dealing with potentially harming high energy terms of your gauge fixed gauge field, but you also have to worry about masses in your theory that suddenly depend on what you do with gauge fixing. Okay. So this choice that I alluded to earlier, where you remove these psi's here from your theory, they are given through sending this psi here to infinity. This essentially makes these chi fields so heavy that they will not impact any dynamics. Okay. So essentially freeze them out by sending this term to infinity. This term will go to 0, and you end up pretty much with that heuristical picture that I presented you earlier with these nice one-point insertions. Okay, so psi goes to infinity would be called unitary gauge. So essentially where you don't really worry about the Goldstone modes anymore. You're just interested in their manifestation as masses of the gauge fields, i.e. longitudinal polarizations, and you forget about the rest. So I'm sure some of you have been using MAD event. Who's been using MAD event before? So quite a few. So the unitary gauge is really the weapon of choice for MAD event because you avoid having random fields that you will not be sensitive to in the final result. However, if you now do electroweak corrections to processes, then of course this will be messed up by neglecting these degrees of freedom. So you can do that as well, but then you really have to worry about when to take limits and how to take them. So this choice is good for tree-level calculations because you deal with an effective subset of degrees of freedom that is relevant to your final answer or to your question. For higher order corrections in the electroweak sector, this should not be used. Okay, so people then use psi equal to 0, for instance, or to 1, moving this term away. Psi equal to 0 will just avoid renormalizing this gauge fixing parameter per se. So there are pros and cons for this.
In what sense is this fixing the gauge if we still have freedom to choose this parameter that gets introduced?
That's a very good question. Unfortunately, I can't really go into too much detail about that. But so the most elegant way is really seeing this at the level of generating functionals. So what the problem with this really is, if you understand this in terms of a generating function, we'll write this into an exponent, is that you integrate over a lot of equivalent field configurations. Okay, so you have this additional gauge redundancy, if you wish. So then you can sort of reverse that by saying you fix the gauge orbit, and you remove that integration, you take it out. So from this full U1 functional integral, you separate out the integration over gauge equivalent configurations. But in order to do this in a nice way, you have to introduce new fields, and those fields are ghost fields. They do not have the right statistics, and they are just bookkeeping parameters. But exactly these new parameters, they enhance the symmetry of your gauge fixed Lagrangian in such a way that the gauge choice you've made will not manifest itself as a modification of your calculation in the end. To always keep in mind, and that, for me that was the hardest bit, growing up in particle physics, said none of these parameters that are written in the Lagrangian have anything to do with observables. Okay, so this is sort of the picture that you come with when you do electrodynamics or you do mechanics, is that these terms have a physical interpretation. But only measurements give them physical interpretations, and there are theories out there that don't even have a Lagrangian density and are only determined at the level of 2, 3-point, and 4-point functions. So these are really the bits that we'll be dealing with quite in some detail when we talk about electroweak precision observables. So I have another 10 minutes, right? Yes? Cool. So let's talk a little bit about the actual theory that we're after. So in the standard model, so electroweak symmetry breaking in the standard model. So as I said, there are some qualitative differences between U1 cases and SU2 cases, but most of it just carries over. So first of all, instead of just looking at U1s, we're looking now at the SU2 times U1. And of course, the Lagrange density that's interesting for us is a -1 divided by 4, WA mu nu, WA mu nu, -1 divided by 4, B mu nu. Okay, so SU2 part, 3 of those, and an additional scalar, an additional U1. Just like in our abelian example, we introduce a scalar field with the non-trivial transformation properties under these gauge interactions. So we throw in a capital phi, which is a 2 1/2. Okay, so depends a little on conventions. So sometimes a good convention to choose for the coupling constant here is with a relative factor of 2 compared to the weak coupling here of the SU2 case. This will become a little bit clearer when we talk about custodial isospin. But for now, we just do not make this choice. So this is hypercharged 1/2 and just a doublet in SU2. Again, our potential will only depend on bilinears in phi dagger phi. So, and just like Q1, you will have a vacuum expectation value that you can now write in SU2 space as a 1 divided by 2, 0, V, okay? So this choice here is arbitrary, okay, that I choose sometimes, depending on what kind of textbook you pick up, say that you have to choose in a lower part the vacuum expectation value in order not to break QED. Okay, that's not right, because this will just single out the unbroken direction. Okay, if I can choose it as whatever I like, I will always end up with one unbroken generator combination of SU2 and U1 that will be unbroken. Okay, so it's just rotating everything in field space, and this freedom in gauge fixing and arc psi gauge is exactly a manifestation of this at the quantum level. Good. So, and then masses arise again from the kinetic term of our scalar sector. So masses then arise from a d mu phi dagger d mu phi with d mu given as d mu minus I g t a w a mu, the SU2 part minus I g prime and the one matrix B mu, right? So this is where it now makes sense what I talked about earlier. We have a 1/2 here. Okay, so maybe 5 minutes. Okay, 5 minutes. So the way this works now is you plug this in. You can hack this into Mathematica. It takes 5 minutes to do that. Don't do it by hand, okay? This is really not worth it. So what this generates is a term or a matrix. So you have if you order these W fields into a vector and you plug in the expectation value of the phi field, you end up with a one form that looks like that, multiplies a big matrix, G squared, G squared, G squared, G, G prime, G, G prime, G prime squared. So the trick is always that you arrange this because it's a real Lagrangian. So this way you can always arrange stuff into a symmetric matrix. And we know that symmetric matrices like that can be diagonalized with, well, essentially you will find an orthonormal basis of linear combinations of W's and B's that will diagonalize exactly this matrix. And of course, these are already trivial in the upper left corner, so we only need to worry really about a two-dimensional matrix, two-dimensional problem, and we know that two-dimensional isometry is just given by one single angle. And this will be the Weinberg angle. So, B mu. So the eigensystem of that is will of course be related to squared masses. Okay, so will be an mw1 squared, which is the same as mw2 squared, which is just these two components. That's just given by g squared v squared divided by 8. Mz squared, which is not really the mz that we're after, because there's a difference normalization in the end after going into the QED symmetric notation. You will get something that is related to g squared plus a g prime squared divided by 8 v squared. So there's a factor of 2 here missing. This is why I only have the approx sign here. And of course we have one unbroken direction, which will identify as the photon mass equal to 0. So the characteristic angle of the two-dimensional isometry that diagonalizes this lower right-hand part is the Weinberg angle. So it's cosine squared theta w, which is given by g squared divided by g squared plus g prime squared. Okay. So when this rotates, W3 and the photons from into the Z's and A field. So this would be C theta minus S theta, S theta, C theta, W3 and B. Okay, so more about this tomorrow, but maybe as a final brain teaser. So this will of course be, when we rewrite this covariant derivative, which will be relevant for the interactions of fermions that we haven't really introduced yet. But these couplings will relate to exactly the neutral and charge current interactions with fermions. Okay, so this cosine square theta w can be defined through interactions of charged fermion interactions and compared them to neutral current interactions. But since we generate all these masses from one VEF, you can see that, there will be an additional factor 4 going away into the normalization of the W's as a complex field, expressing quantum electrodynamics most transparently in the Lagrangian. There will be an additional factor of 2. So what we'll see in the end, if you take the WZ mass ratio, you have the same ratio of couplings as you have here in the isometry. So, and that's quite, it sounds almost trivial, but actually it's completely non-trivial, because the diagonalization here of the isometry that does that does not need to be related in any sort of way to the eigenvalues of the diagonalized system. So there seems to be a delicate interplay between the 2 by 2 diagonalization matrix and the mass eigenvalues. And that directly translates into comparisons of observables, okay? So you measure the W mass peak, you measure the Z mass peak, you take the ratio, you measure the charge current interactions and the neutral current interactions, you take the ratio, and then the prediction of the standard model is that these quantities should be equal. Yeah? And this is really highly precisely measured at the Large Electron Positron Collider. And it really has to do with the fact that we break electroweak symmetry here with a doublet. But we'll talk about this in a little bit more detail tomorrow. Okay, are there any questions? Yeah.
What about mass term 0? Suppose the mass term is 0 and you are introducing some high dimensional term with Fourier sign and you make it.
I'm not 100% sure if I can follow. So your
The mass term,
Yeah.
square term.
Yeah.
There are two possibilities you take, like greater than 0 and less than 0.
Mm-hmm.
I am talking about exactly mass square term equals to 0.
Yeah.
That is also a viable solution because if you include extra higher order term with opposite sign, then you can get
Yeah.
similarly.
Yeah, so just to repeat the question, what we've been talking about here is essentially telling the theory to break by choosing mu squared to be smaller than 0. We're not interested in mu squared bigger than 0 because that's not the situation that we like to be in. So what about mu squared exactly to 0? That's a delicate business, first of all, because that term is not protected through any symmetry. So all of these terms that we've written down here, as all terms in the Lagrangian, they are scheme dependent, which means they depend on whatever kind of renormalization, regularization scheme I choose. So having something like conformal standard model that relates to that, and you trigger electroweak symmetry through radiative corrections. This is possible. So this goes through like the Coleman-Weinberg potential type of thing. Maybe we have the time to talk a little bit about composite Higgs stuff, so it's related to that as well. That will, in general, predict masses that are not really compatible with what we've seen. So it has to be really a sizable vacuum expectation value, and you can't trigger this straightforwardly through loop effects as such. There are different attempts to do that. You can always, the Higgs has this special property that you can form a complete standard model singlet with it, and there are only, so many choices really in the standard model to sort of come up with standard model singlet operators. One would be mixing with a right-handed stereoneutrino as a bit of your personal flavor, whether you consider this part of the standard model or not. U1 mixing, which is tightly constrained through electroweak precision measurements. But of course, H dagger H or phi dagger phi is a complete standard model singlet, so you can couple this to whatever sector you like. So you can do the Coleman-Weinberg idea there. You do it at a higher scale, and you sort of mediate this to the visible sector. So a lot of people have been thinking about these sorts of scenarios. One of the crucial issues really is that setting the mass term or this mu squared term to 0, and that relates directly to the hierarchy problem, is that the Higgs mass is a super relevant operator. So setting that to 0 will only stay 0 if I use dimensional regularization. So you can say that I want classically conformal theories, so I can start with mu squared equals to 0, but they don't need to be. What does classic conformal invariance really mean in the quantum world? So you can start thinking about these things a little. And I would say that there are strong opinions on either side, but the answer is not very straightforward here. Okay, so but we can talk about this over wine, probably much better. Any other questions? Yeah.
Mu square cannot be 0 because it's not protected by any symmetry, but we can impose symmetries like the symmetry or R symmetry, and then mu can be, this mu square term can be 0, and then it can get a non-zero value.
Yeah. Well, I'm saying so that the was a comment rather than a question. So we can enhance the symmetry and setting it to 0, and then having it like protected but hierarchical. Is this, if I understand you correctly?
Yeah, I mean, then if the symmetry breaks, then this square will get to 0.
Yeah, so this would exactly dial into these ideas of composite Higgs theories, which are difficult to achieve, and at the moment, in the low energy side of things, we base all of our implications on nonlinear sigma model stretching. So it becomes essentially the old Coleman-Weinberg idea plus some additional phenomenological facts of reality, like non-oblique corrections and oblique corrections and stuff like that. You blend that with group theory. So people here in Boulder work very hard on trying to see whether this can work in an ultraviolet complete sort of way. So all composite Higgs models that are currently looked for at the LHC by Atlas and CMS, and minimal composite Higgs models 4 and 5, so very romantic names, they have no known non-supersymmetric ultraviolet completion. So of course you can always argue that these things are possible, but it's very difficult to go past the low energy effective theory world in that. So if you have a 0 mu squared, and you choose a scheme that's not dimensional regularization, then you will induce a new mu squared. So it only becomes a multiplicative renormalization in renormalization and regularization schemes, more like, that respect a maximum amount of symmetries. Okay, so if I regularize my theory with a cutoff, that's not good for electroweak interactions, but I could do that. Then I would introduce a mu squared as proportional to the cutoff. This is exactly the problem of the hierarchy problem. But it also tells you that the hierarchy problem is manifestly something that's scheme dependent. So it tells you that something is funny, something smells funny, but you can't really pinpoint what it is. Yeah. But we talk about this in a little bit more detail, I hope, in the forthcoming lectures. I'm told to shut up. Okay, fair enough. So thanks very much.